In this video, we're going to look at geometric behavior of nonlinear autonomous systems. We're going to find the equilibrium points for nonlinear autonomous systems. We're going to compute the Jacobian matrix. And if you're in my Calc 4 class, you're like, woo, Jacobian, how exciting. Determine the types of equilibrium points for nonlinear autonomous systems. And we're going to sketch phase portraits by hand for nonlinear autonomous systems. Now, to solve nonlinear autonomous systems of differential equations is pretty difficult, so we're not going to do that. But we can analyze them because they do come up a lot in biology and other areas of study. So to do this, we're going to look specifically at two things. We're going to look at the equilibrium or the stability points and the phase diagrams. And we're going to relate x1 and x2. So let's start with some definitions. Always the definitions. The null lines for x prime in the system of x prime, which is a function of x and y prime, that should be a comma right there, which is equal to a function of g of x and y, are the curves in the phase plane on which the x prime is equal to 0. These can be set by putting our function f of xy equals to 0 and solving explicitly for x as a function of x or x as a function of y. Similarly, we do the same things for g of xy is equal to 0. Note, any point along the null line for x prime, the tangent vector of f of xyi, g of xyj in the phase plane will be vertical. And along the null lines for y prime, the tangent vector will be horizontal. And that kind of makes sense, especially if you think about it in terms of Calc 4. A couple of things you might want to note is that the null lines intersect at the location of the equilibrium points. So suppose x sub 1 represents a population of foxes and x sub 2 represents a population of rabbits, both after t weeks. Find the null lines for this. The derivative of x sub 1 with respect to t and the derivative of x sub 2 with respect to t are given here. Then determine what happens at the equilibrium points and interpret the results. All right, so here we go. We're going to just follow through what it said is I'm going to set my first derivative equal to 0. So I have 0 is equal to 0.4 x sub 1 minus 0.002 x sub 1 x sub 2. And I can easily factor out a decimal. I'm going to factor out 0.002 and an x sub 1 because they're common. So this is 0.002 x sub 1. And then what I end up with is 200 minus x sub 2. And we know this is equal to 0. So we know that x sub 1 is equal to 0 and x sub 2 is equal to 200. Now, if I put that into these two values into my second derivative here, if x sub 1 is equal to 0, then I have 0.03 x sub 2 is also equal to 0. So x sub 2 is equal to 0 when x sub 1 is equal to 0. So we have our first 0, 0 ordered pair. Now, if x sub 2 is equal to 200, and again, I'm going to put it back into this equation up here, then I'm going to get 60 minus 0.2 x sub 1 is equal to 0. So x sub 1 is going to equal 300. So my second ordered pair I'm going to get is 300, 200. So my null lines are these. This is x sub 1, and this is x sub 2. Now, if you remember, when we were graphing these eigenvectors, we label this x sub 2 axis. This is the x sub 1, x and y if you prefer, but that would be better. If I were to graph the null lines, that I have this line, which is x sub 2 is equal to 200, and I have this line, which is x sub 1 is equal to 300, and right here is that point of intersection, which also we can see is right here. Well, that's the easy bit. Now we want to think about what's going on. So I'm going to break up this quadrant very easily into the upper left, the upper right, the lower left, and the lower right. And so this way I can talk about what's happening in each one of those positions. Now, when I choose points, I'm obviously not going to choose points that are on the null line, so I'm going to choose some point in here in which my x sub 1 is less than 300 and my x sub 2 is greater than 200. So let's do, say, if x sub 1 was equal to, say, 200 and my x sub 2 was, say, equal to, have to be bigger than 200, so let's do 300, so that they've actually switched position. So I'd be looking at something right about in here, right? Some point right about in there. So what I'm going to do then is I'm just going to put these into the two derivatives and then determine what's going on. So I go back and I say, okay, well, my derivatives, d of x sub 1 dt, is going to be equal to 0.4 x sub 1, which is 200, then minus 0.002, 200 multiplied by 300, and I'm going to just get my calculator out, and this is equal to a negative 40. Now I'm going to do the same thing for the d of x sub 2 over dt, and this will equal to the 0.3 multiplied by my, let me go back up there, 0.3 multiplied by my 200, because that's my x sub 2, no, sorry, my x sub 2 should be 300, and then minus 0.001 multiplied by my x sub 1, so 200 and 300. Once again, I'm going to get my calculator out, and this is a positive 30. Now, remember, the way that we set this up is that x sub 1 represents the population of foxes. So up in this quadrant, my population of foxes are decreasing. And since x sub 2 represents the population of rabbits, that means if I choose some ordered pair point up here, the population of my foxes, which is my x sub 1, is decreasing over time. And the population, because this is positive, of my rabbits are increasing over time. Well, then we repeat this for all of the other quadrants, and then this is what the end result is. So we know what these quadrants are, and we're going to repeat this process until we get a better idea of what each one is doing. Now, in this upper left quadrant, we knew that the x sub 1 was decreasing as x sub 1 increased. So as x sub 1 decreased as the number of rabbits increased. Because remember, these were my rabbits and these were my foxes. Then in this quadrant here, the upper right quadrant, if I choose some initial values in that upper right quadrant, then I know both my foxes and my rabbits are decreasing because they're both showing up negative. Down here in my lower left quadrant, as my foxes increase, my rabbits are also increasing to that equilibrium point. And then in this lower right quadrant, I ended up with them being a negative in the x sub 2 in the rabbits. The rabbit population is decreasing as the foxes increase. And then we didn't have to solve for anything really other than if I was trying to decide what's going on with this initial value problem, depending on which quadrant my initial value landed in. If this was my derivatives with respect to time, then I can tell you what's going on with the population of rabbits versus foxes if I were to have an initial value in this quadrant, this quadrant, this quadrant, or this quadrant. Now, I just want to say as we continue with this, it's not necessarily going to be nice quadrants like that, but I'm still going to label them as quadrants, or however I need to label them, just so that I can keep track of what's going on. So now let's suppose that this represents the population of foxes. X1 is still my foxes. X2 represents my rabbits. And now we're going to find the null lines for this example. So we're going to start out with this first, the derivative of x sub 1 with respect to time. And you can see that x sub 2 is in all of them. So it's a factor of all of them. So I'm going to factor that out. So I have x sub 2 minus x sub 1 minus 1 is equal to 0. And I'm going to do the same thing with the derivative of x sub 2 with respect to time. And so I notice that it all has an x sub 1 that is constant, is the same. So I have x sub 1. And then I have 2 x sub 1 plus x sub 2 minus 7 is equal to 0. And I'm going to ignore the fact that when x sub 2 is equal to 0 and x sub 1 is equal to 0, that means we have populations of nothing. So that's nothing interesting. But I do have this x sub 2 minus x sub 1 is equal to 1. And I do have this x2 x sub 1 plus x sub 2 is equal to 7. So basically I got these couple of lines. Now remember, my x sub 2 is the one that I would consider the y. So to graph these, I'd have x sub 2 is equal to x sub 1 plus 1. And this x sub 2 would equal negative 2x plus 7. So once again, I'm going to go to my x-axis. So this would be my x sub 2 axis. It would be my x sub 1 axis. And I'm going to graph these two. So I have x sub 2 is a positive slope with an intercept of 1. So this is my x sub 2 is equal to x sub 1 plus 1. And then I'm going to graph the x sub 2, and then so I'm going to cross at negative 7, start at negative 7 as the intercept, and I'm going to come down. So this is x sub 2 is equal to negative 2x plus 7. And then to find this point of intersection, I'm going to just solve like I normally solved when I have a system of equations, however you prefer to solve. So I have, I'm going to just do a substitution here because it's not too bad. I'm going to substitute this into here. So I have 2x sub 1 plus x sub 1 plus 1 is equal to 7. 3x sub 1 is equal to 6. X sub 1 is equal to 2. So I find that this is the point 2, 3. Now again, I need to find out what's going on with the populations. And I'm just going to label my quadrants. I'll label it as 1, 2, 3, and 4. And so I'd start with quadrant number 1. And I'm going to choose a point that's in quadrant number 1. And so I would choose, let me see, I would choose the point maybe 1, 3. So it'd be somewhere about right there. So about right here is where I'd be choosing. So I know I'm in that quadrant. And I put in 1, 3 back into the d sub 1 of dt. And so I get x sub 2 squared, so this is going to be 3 squared, minus 1 multiplied by 3, minus x sub 2, which is 3. And so I get this to be a positive number. Do the same thing with the dx sub 2 of dt. And I get 2 multiplied by x sub 1 squared, which is 1 squared, plus 3 multiplied by 1, minus 7. And so I end up with the x sub 2 is negative. Okay, so, and I would continue this for all of the points. And then I would then say, well, wait a minute. I know that in this quadrant right here, my x sub 1 is increasing over time, but my x sub 2 is decreasing. So I'm just going to erase this so I can put in my arrows in the appropriate places. And so I end up, this is going to come down into this point. I'm going to find that this one's going to go in that direction. This is going to go in this direction. And this is going to go in that direction. And then I can tell you what's going on with the population of rabbits and foxes in this example. So the summary, just summarize this up. Give me a nice little algorithm. Set the derivatives equal to 0. Assume x sub 1 and x sub 2 are non-zero. Then you'll get some sort of line. Solve the system. In other words, you're going to choose a point of the equilibrium. Or actually, you're going to find the point of equilibrium. You're going to then plot your lines and the point of equilibrium. I actually plotted my lines first up here, but it's all good. And then you're going to pick a point in each of the regions, plug it into the system, and that will tell you what's happening with the arrows, how you're going to put the arrows. And then understand what it means when you get done. I mean, that's the most important thing. Why are we doing this? It's so we can understand what it means. Now, as promised, Jacobian, here it is. Well, here's the reasoning behind it, and then we'll get to it. About 100 years ago or less, somewhere around there. So in mathematical terms, not very long ago. The Hartman-Grobin theorem essentially says that if the equilibrium point x bar y bar is moved to the origin in the phase plane, making these variable replacement, u is going to be equal to x minus x bar being the x part of the equilibrium point, and v is equal to y minus y bar being the y part of the equilibrium point. And if all the nonlinear systems in u and v are discarded, then close to this equilibrium point, the nonlinear system will behave pretty much like a linear system in u and v at u and v is equal to 0. Because x bar and y bar are constants for our system of equations on these examples, u and v are functions of t. That means the derivative of u of t with respect to t and the derivative of x of t minus x bar of d of t is equal to d of x dt. Similarly, we get this. And f and g are sufficiently differentiable. They can be expanded in the Taylor series about this. So we end up with this. Since x bar y bar, the function of x bar y bar, and the function of g of x bar y bar are both equal to 0, then x prime is equivalent to u prime, which is approximately equal to the derivative of f with respect to x, v of t, and the derivative of x with respect to y, v of t. Similarly, that y prime is equivalently equal to u prime, which is approximately equal to the derivative of g with respect to x, v of t, plus a derivative of g with respect to y of v of t. And we get this lovely Jacobian. A couple of more definitions, and then let's go through an example. An equilibrium point for the autonomous system of equation is called the hyperbolic equilibrium if the Jacobian at the equilibrium point has no eigenvalues with real zero parts. This theorem that we have tells us that if the trace of the Jacobian, comma, the determinant of the Jacobian lies inside the region of the trace determinant plane, then a small region about the equilibrium points of our nonlinear system has the same type of behavior as a corresponding linear system around 0, 0. Once the Jacobian matrix is computed, all the equilibrium points can be easily tested. So here's an example. Compute the Jacobian. If this first equation is x prime is x sub 1 prime, and x sub 2 prime is that second equation, then my partial derivative of f, which is the first equation, the partial derivative of f with respect to x sub 1 is going to be equal to 0.4 minus 0.002 x sub 2. My partial derivative of g, that's my second equation, not f, partial derivative of g with respect to x sub 2 is going to be 0.3 minus 0.001 x sub 1. I'm going to do the partial derivative of f with respect to x sub 2, partial derivative of f with the x sub 2. I'm going to do the partial derivative of g with x sub 1. The partial derivative of f with x sub 2 is just going to be negative 0.002 x sub 1. Partial derivative of g with x sub 1 is just going to be negative 0.001 x sub 2. Now I'm ready to do my Jacobian, and as you know, when I do my Jacobian, it doesn't really matter the order as long as we're consistent. So I'm going to have f and g here, x sub 1 here, x sub 2 here. This just helps me with my keeping order. So this is going to be 0.4 minus 0.002 x sub 2. Probably should give myself a little bit more space here. And then my Jacobian with f with respect to x sub 2, so negative 0.002 x sub 1. Then my g with respect to x sub 1, so 0.001 x sub 2, and then the other one, which is 0.3 minus 0.001 x sub 1. Now, if I were to evaluate this at my equilibrium point, which is 300, 200, and we found that from earlier, then my Jacobian becomes this. It's going to be 0 here. This will be a negative 0.4. This will be a, and that should be a negative right there, a negative 0.2. And this will becomes a 0 here as well. This Jacobian has a trace of 0 and a positive determinant. And then I can just go look at, if you remember from yesterday's video or 65253 video, I can tell you everything that you need to know about this on my trace determinant plane with a trace of 0 and a determinant that is positive. And I'm going to let you do the Jacobian for this one, and that's it for this video. Nice short one.